Okay, so DeepSeek just unveiled something truly mind-bending. A massive AI model, 671 billion parameters.
Which is huge.
Exactly. But somehow it runs faster than models a tenth of that size.
How does that even work?
Well, the secret apparently is that it only activates like a small fraction of those parameters, just 37 billion at any given moment.
Hmm.
Think of it like, owning this enormous library, but for every question, a brilliant librarian instantly points you to one perfectly curated bookshelf.
Okay, so super efficient targeting.
Incredibly efficient. And as if that wasn't enough, there's another breakthrough, multi-head latent attention, or MLA.
Right, I saw that.
It just made models an astonishing 57 times more memory efficient.
57 times.
Yeah, while actually improving performance.
Wow, okay.
So welcome to 2025, I guess, where the AI arms race isn't really about who builds the biggest model anymore. It feels like it's about who builds the smartest. We're doing a deep dive today into what I'm calling the architecture wars. They seem to be fundamentally reshaping artificial intelligence right now.
Yeah, it feels like a shift is happening.
Because, 7 years ago, the transformer architecture came out, that famous attention is all you need paper.
Right, the foundation for everything.
Exactly. It became the blueprint for basically every major language model, from GPT to Gemini, all of them.
Ah,
And what's really remarkable, I think, is despite trillions, literally trillions, in investment and these huge leaps in capability,
yeah.
that basic blueprint hasn't fundamentally changed.
Still the same core ideas.
And yet now we see models like DeepSeek v3 topping the open source leaderboards. We see Qwen 3 matching GPT-4 performance, but with way less compute.
Right, and tiny models running on phones.
Exactly. Sophisticated AI on your phone.
It really begs the question then, what's truly happening behind the scenes? How are these seemingly small, incremental architectural tweaks leading to such dramatic leaps in performance?
Yeah.
It suggests maybe we've been misunderstanding what progress in AI actually looks like.
That's precisely what we want to unpack in this deep dive. We'll explore why this memory bottleneck has become this sort of hidden crisis limiting AI.
Yeah.
Then we'll unravel how these mixture of experts architectures let models be both massive and efficient.
The MOE approach, yeah.
We'll get into that groundbreaking 57x memory improvement from MLA and how that could, maybe democratize AI.
Make it more accessible.
And finally, we'll discuss why the next big AI breakthrough might actually come from making models smaller, or at least smarter, not just bigger. So, as we get into it, maybe think about this for yourself. When you picture AI progress, are you seeing bigger and bigger models, or are you starting to picture smarter architectures? Let's dive in. Okay, let's start with maybe a reality check about where AI development is right now. Because it's probably not what most people think when they hear about, trillion parameter models.
Yeah, it's quite interesting. Sebastian Rochka, who's a real leader in thinking about LLM architecture,
Right.
he pointed out something crucial recently. Despite years of really intense development, modern LLMs, from GPT-2 right up to this new DeepSeek v3, they remain, in his words, structurally similar to the original transformer.
Still, after all this time.
Pretty much.
Yeah.
The core building blocks are still there. You've got self-attention.
Which helps it weigh word importance.
Exactly. You've got feed-forward networks, which process those insights.
Uh-huh.
And layer normalization, which kind of stabilizes the whole learning process.
Uh-huh.
Those fundamental pieces haven't really changed.
Wow. And yet the scale has just exploded, right? GPT-1 was what, 117 million parameters?
Tiny by today's standards.
And then GPT-3 hit 175 billion.
A huge jump.
And now, current models are pushing towards 1 trillion parameters. So same basic blocks, just exponentially more of them.
And that's precisely where the challenge comes in. As these models get bigger, they hit this wall. The memory bottleneck.
The hidden crisis you mentioned.
Yeah, it's hidden, often overlooked, but incredibly expensive.
Yeah.
And at its heart is the key value cache, the KV cache.
Okay, what is that exactly?
Think of it like the transformer's short-term memory. It stores these concise summaries of every word, every token it's processed so far in a conversation or a document.
Got it.
But the critical part, the part that causes the problem, is that this memory grows quadratically with the length of the text, the sequence length.
Quadratically. Okay, unpack that.
It just means if your conversation doubles in length, the memory needed doesn't just double, it quadruples.
Wow.
Triple the length, 9 times the memory. It escalates incredibly fast. And that quickly becomes unsustainable for long documents or complex back-and-forth interactions.
So, okay, what are the real-world impacts of that? I mean, beyond the technical side.
Well, imagine trying to feed a massive legal document into an AI, or having a really long, detailed chat with an AI assistant.
Right.
The memory requirements just explode. It makes deploying the model either technically impossible on certain hardware or just prohibitively expensive. It's a massive economic barrier, not just a tech one.
And Microsoft, didn't they have an estimate on apps?
Yeah, Microsoft estimates something like 750 million apps will be built using LLMs by 2025.
Wow.
And a huge number of those are running smack into these memory walls. It stops them from being deployed widely or affordably.
Which is exactly why this DeepSeek achievement is so, well, remarkable. It signals maybe a shift in thinking, right? Because this is where things get really interesting. DeepSeek's breakthrough isn't just about size. It's about building a model that's fundamentally more efficient.
Exactly. And that brings us to multi-head latent attention, MLA. To really get it, let's compare it to the traditional approach, multi-head attention.
Okay.
Traditional attention stores every single key and value tensor in memory. It's kind of like keeping every page of every book you've ever read spread out on a giant table.
Just in case you need one tiny detail later.
Precisely. It's incredibly memory intensive. MLA's genius is, well, it's quite elegant. It compresses these key value tensors into a smaller, lower dimensional space before it stores them.
Okay, so it summarizes them first.
Kind of. Imagine that perfect filing system we talked about, compressing entire books onto index cards, but keeping all the crucial info, the important context. That compression is the key.
And the results you mentioned, 57 times less memory.
It's really dramatic. MLA achieves an astonishing 57 times less memory usage compared to the standard multi-head attention.
That's huge.
And it's even 12 times less memory than other optimization techniques like grouped query attention.
Which was already supposed to be an improvement, right?
Exactly. GQA was a step, but MLA is a massive leap beyond that. It just fundamentally changes the memory footprint.
And you said it doesn't just save memory, it performs better.
That's what's particularly striking. It's not just an optimization trade-off where you sacrifice a bit of performance for efficiency. MLA actually performs better than the traditional attention mechanisms in their tests.
That's rare. Usually there's a trade-off.
It is rare. Getting both efficiency and a performance boost like this is pretty significant.
So practically speaking, what does this unlock?
Well, models that used to need these massive server farms just to handle, say, long conversations or documents, they can now potentially run on much smaller, much more accessible infrastructure.
Okay.
Applications that were just too expensive before because of the memory costs, they suddenly become viable, economically feasible.
It opens up new possibilities.
Totally. And this isn't just theory. DeepSeek v3, the model using MLA, is currently topping the chatbot arena open source leaderboard. It has an ELO score of 1382, which is really impressive.
So it's validated in the real world.
Yeah, it shows this architecture works and works well. But MLA is only one piece of DeepSeek's puzzle.
Great, there's the other part.
The other part is maybe even more fascinating, and it's changing how we think about model size altogether.
Mixture of experts. MOE.
Exactly.
Okay, break that down. And the analogy you used before was like building an advisory team.
Yeah, I think that works pretty well. Imagine you need advice for a complex project. You could hire a few generalists who know a bit about everything.
Okay.
Or you could hire specialists, a finance expert, a legal expert, a marketing guru. And for each specific decision, you only talk to the relevant expert.
Right. You don't need the whole team for every single question.
Precisely. That's basically what mixture of experts does inside an AI model.
So how does DeepSeek v3 use it? It has the 671 billion parameters total.
Right. But those parameters are organized into 256 different experts, distinct neural network modules.
Okay.
Now, for any given input, like for every single word or token, it processes a routing mechanism inside the model, dynamically activates only a small subset of those experts. In DeepSeek's case, it's just 9 experts.
Only 9 out of 256.
Yeah. So for any specific task, only about 37 billion active parameters are actually doing the computation at that moment.
Wow. So you get the knowledge capacity, like the potential knowledge of a 671 billion parameter model.
Exactly. All that stored information and nuance.
But with the computational cost, the inference speed of a much smaller 37 billion parameter model.
It's like getting the wisdom of the huge library, but only paying the running costs for that one bookshelf you need right now. It's incredibly efficient.
You get your cake and eat it too, basically.
Pretty much, yeah. It's a very clever way to scale knowledge without scaling cost proportionally.
And DeepSeek isn't the only one doing this, right?
Not at all. This MOE approach is gaining serious traction. Alibaba's Qwen 3 family of models uses it heavily.
Okay.
Mistral's Mixtral 8x7b was a huge open source success story that really popularized MOE for many people.
Right, that made a big splash.
And there are strong reports, pretty widely believed, that even OpenAI's GPT-4 uses in MOE architecture internally.
Interesting. So all the big players are moving this way.
It definitely looks like a major trend, yeah. A fundamental shift in design philosophy.
And the practical benefits are pretty clear then. Lower costs, faster responses.
Significantly lower inference costs, yes. Faster response times for the user. And crucially, the ability to keep making the models more knowledgeable, scaling up that total parameter count without the computational requirements exploding in the same way.
So how does it actually work? How do the experts specialize?
Well, during the training process, different experts naturally start to specialize in different kinds of tasks or data patterns.
Like one gets good at coding.
Exactly. One might become really good at analyzing code, another might excel at creative writing styles, another might develop strong mathematical reasoning skills.
Okay.
And then there's a lightweight routing network that also gets trained. Its job is to look at each incoming piece of information, each token, and predict which experts are most likely to handle it well.
So it directs the traffic.
Precisely.
Yeah.
It directs the input to the most relevant specialists for that specific task. It ensures the model uses its resources efficiently and leverages the specialized knowledge effectively.
That makes sense. And connecting this back to the economics, you mentioned that Microsoft prediction.
Right. Henry Jams at Microsoft predicting 50% of digital work could be automated by current tech.
That's a huge number.
It is. But that kind of large-scale automation is only really feasible if it's cost-effective.
And MOE helps make it cost-effective.
Exactly. MOE architectures, by being so much more efficient at inference time, are a key enabler for making widespread AI automation economically viable for businesses and, everyone else.
But MOE and MLA, while they're getting headlines, they aren't the only architectural tricks people are using, right? There are other ways teams are chasing efficiency.
Absolutely. DeepSeek's approach is powerful, but it's definitely not the only game in town. Other teams are tackling this efficiency challenge from different angles.
So what else is out there? What are some other strategies?
Well, take Google's Gemma 3 model. They use something called sliding window attention.
Sliding window. Okay, what's that?
Instead of having the attention mechanism look at the entire input sequence at once, which is what causes that quadratic memory scaling, it only looks at a local window of tokens around each position. Think of it like reading that long book, but you're only really focused on the current page and maybe a few pages just before and after it.
Okay, so it limits the scope.
Exactly. This dramatically reduces the memory needed, especially for very long sequences, like processing entire books or very long conversations.
But does it lose context if it's only looking locally?
That's the clever part. While it might seem like it would lose long-range context, these models are surprisingly good at inferring broader relationships, often through how information propagates through the layers. It maintains a lot of the reasoning capability while being much more memory-friendly for length. It's a smart trade-off.
Interesting.
Okay, what else? Then there's small M3, which is pretty radical. They went with no positional embeddings.
No positional. Wait, transformers normally need to know the position of words, right? Like dog bites man versus man bites dog.
Traditionally, yes. Positional embeddings were considered essential for the model to understand sequence order. Small M3 just gets rid of them entirely.
And it works.
Surprisingly well. It maintains competitive performance. This really challenges a core assumption about how transformers must work. It suggests maybe the models can learn sequential relationships implicitly from the context itself without needing explicit position markers.
That could open up totally new design possibility.
It really could. If positional embeddings aren't strictly necessary, architectures could become even leaner, maybe more flexible. It's a fascinating line of research.
Wow. Any other maybe more subtle changes happening?
Yeah, there's also a lot of ongoing experimentation with things like normalization layers. You see models like Olmo 2 and Gemma 3 moving towards post-norm configurations, or using things like 2K norm.
Okay, those sound technical. What's the goal there?
Mostly about improving training stability and efficiency. These might seem like minor implementation details, how you normalize the values flowing through the network, but they can make training faster, more reliable, especially when you're dealing with really large models. They contribute to the overall robustness and performance.
So even these smaller tweaks add up. It feels like there's a fundamental shift happening instead of just making everything bigger.
Exactly. It's less about brute force scaling and more about engineering elegance. Teams are optimizing every single component, squeezing efficiency out of every part of the architecture.
And the impact is real. Like, costs are actually coming down.
Oh, definitely. Wired reported recently that inference costs, the cost to actually run these models after training, are dropping by roughly an order of magnitude each year.
An order of magnitude, that's huge.
It is. And these architectural innovations, these efficiency gains, are a major driver of that trend. It fundamentally changes the economics of deploying AI.
It really makes you wonder. Maybe the biggest breakthroughs won't come from the companies with the absolute biggest compute budgets.
Right. Maybe they'll come from the teams with the cleverest architectures, the most elegant solutions to these efficiency problems.
Which brings us to a really important point. What does all this efficiency mean for accessibility? Who gets to build and use this stuff now?
Yeah, and this is where it gets truly exciting, I think. These innovations aren't just making AI technically better, they're making it accessible to basically everyone.
How so?
Well, we're seeing concrete examples already. You have models like TinyGPT or TinyGPTV for vision. They can run sophisticated AI tasks using just 8 GB of memory.
8 gigs, that's standard laptop territory.
Exactly, it's laptop territory, and it's even getting into mobile phone territory. This dramatically lowers the barrier to entry. You don't need a supercomputer anymore.
So does this mean developers in, say, regions without massive cloud data centers?
Yeah, or researchers at universities with tighter budgets.
They can now actually build and experiment with state-of-the-art or near state-of-the-art models.
Absolutely. The playing field is leveling out significantly. Innovation isn't just concentrated in a few massive labs anymore. It can come from anywhere.
And for startups, this must change the game entirely.
Immensely. You no longer necessarily need millions in upfront infrastructure costs to compete. Clever architectural choices, efficient implementation that becomes your competitive edge rather than just deep pockets. It fosters real innovation based on ideas, not just resources.
And we're seeing the results, like AI popping up in new places.
For sure. AI is now appearing in regular mobile apps, in embedded devices, in edge computing scenarios. Think AI running locally on sensors or machines, places that were simply impossible just a couple of years ago because the models were too big and power hungry.
We're moving towards AI being kind of everywhere.
Pretty much. And there's another angle here too, the environmental one.
Ah, right. Efficiency means less energy.
Exactly. More efficient models mean lower energy consumption for every calculation they perform. As AI becomes ubiquitous, deployed across billions of devices and interactions, the cumulative energy savings from these architectural efficiencies could be absolutely massive. It's a quieter, but potentially huge win for sustainability.
That's a really important point, and it probably changes business models too.
Definitely. Companies used to face this stark choice. Either you get a cheap, limited AI, or you pay a fortune for a powerful one.
Right.
Now, the paradigm is shifting towards efficient and powerful. You can have capable AI without the crippling cost. This opens up entirely new markets and applications that just weren't viable before.
And ultimately, all this accessibility, it must speed things up.
It accelerates innovation like crazy. When more people, more diverse groups can experiment with advanced AI, you inevitably get more diverse applications, more creative solutions nobody thought of before, and much faster cycles of improvement across the whole field. It's creating this positive feedback loop for progress.
But it's not like all the problems are solved, right? As we look ahead, say, to 2026 and beyond, there must be new challenges, new frontiers for these architecture wars.
Oh, absolutely. We're definitely not at the end of the road here. New challenges are constantly emerging that might require totally different architectural thinking.
Like what? What's on the horizon?
Well, one major trend is the push towards models that are much better at reasoning. Explicit, step-by-step reasoning.
Okay, like DeepSeek R1.
Exactly. Models like DeepSeek R1 are ranking highly on leaderboards specifically for their reasoning abilities. But here's the trade-off. Reasoning often seems to require more computation, more steps, which kind of conflicts with that drive for pure efficiency we just talked about.
Ah, so there's a tension there.
There is. Future architectures might need to be more dynamic. Maybe they need modes, a fast, efficient mode for quick answers, and a slower, more deliberate, computationally intensive mode for complex reasoning tasks. Designing that switch effectively is a new challenge.
Interesting. What else?
Another potential game changer is synthetic data.
AI generating its own training data.
Yeah. As models get better and better at creating high-quality training data for themselves, the requirements of the architecture might change dramatically. We might see designs optimized specifically to learn incredibly well from synthetic data, which could be different from architectures optimized for human-generated text.
So the data source could influence the structure.
It very well could. And then, of course, there's multimodality.
Right, handling text, images, audio, video altogether.
Exactly. Each of those data types, images, sound waves, video frames, has very different computational characteristics than text. Building architectures that can seamlessly, efficiently process and integrate all these modalities at once, that's a huge architectural challenge that we're really only just starting to scratch the surface of. The complexity just explodes.
But the potential payoff is huge, too.
Immense. Truly understanding the world requires integrating all these senses, so to speak.
It really feels like we're still in the early innings of architectural innovation then. Today's solutions like MLA and MOE are brilliant. They solve today's problem.
Right, they're incredibly ingenious for the current bottlenecks.
But tomorrow's challenges, reasoning, synthetic data, multimodality, might need completely new ideas, solutions we haven't even conceived of yet.
It's entirely possible. The field is moving so fast, the next big breakthrough could come from anywhere.
So it makes you wonder, what do you think? What will be the next major architectural breakthrough? Will it be optimizing for reasoning? Nailing multimodal efficiency? Or something totally unexpected? Okay, so let's try and bring this all together. 7 years back, attention is all you need kicked off the transformer revolution, setting the blueprint for AI as we knew it.
The age of scale, you could say.
Yeah, but today it feels like we're witnessing maybe the efficiency revolution. It's proving that sometimes the biggest breakthroughs don't come from just making things bigger, but from making them fundamentally smarter, more elegant.
Smaller components, cleverer interaction.
Right. And these architecture wars, they aren't just about technical details, about shaving off milliseconds or saving RAM. They feel like they're really about democratizing access to intelligence itself.
Making powerful AI available to more people, more applications.
Exactly. In a world where, maybe the most powerful AI might soon run comfortably on your phone, the big question isn't just who has the biggest model anymore.
No, the question becomes,
Who has the smartest one?